For the remainder of this unit, I'm going to talk about linear dimensionality reduction, where the idea is that we're given data points like this, and we seek to find a linear subspace to which to project the data. In this case, I would submit this is probably the most suitable linear subspace. So we remap the data onto the space over here with x1 over here and x2 over here, then we can capture the data in just one dimension. The algorithm is amazingly simple. Number one, fit a Gaussian. We now know how this works. The Gaussian will look something like this. Number two is calculate the eigenvalues and eigenvectors of this Gaussian. In this Gaussian, this will be the dominant eigenvector, and this will be the second eigenvector over here. Step 3 is pick those eigenvectors whose eigenvalues are the largest. And step 4 is to project the data onto the subspace of eigenvectors you chose. Now, to understand this, you have to be familiar with eigenvectors and eigenvalues, but I'll give you an intuitive familiarity with those. This is standard statistics material, and you'll find this in many linear algebra classes. So let me just go through this very quickly and give you an intuition how to do linear dimensionality reduction. Suppose you're given the following data points. Your x's are 0, 1, 2, 3, and 4 for x1, and 1.9, 3.1, 4, 5.1, and 5.9. These are essentially 2, 3, 4, 5, 6, but slightly modified to define actual variance over this dimension. If I draw this in here, what I get is a set of points that doesn't quite fit a line, but almost. There's a little arrow over here, a little arrow over here, and here and here. Now the mean is easily calculated. It's 2 and 4. The covariance matrix looks as follows. Notice the slightly different covariance for the first variable, which is exactly 2, to the second variable, which is 2.008. The eigenvectors happen to be 0.7064 and 0.7078 with an eigenvalue of 4.004, and the second one is orthogonal with an eigenvalue much smaller. So obviously this is the eigenvector that dominates the spread out the data points. And if you look at this vector over here, and you center it around the mean, which sits over here, and it's exactly this vector shown over here. Whereas this one is the orthogonal vector shown over here. So this is the single dimension with a large weight explains the data relative to any other dimension which has a very small eigenvalue. I should mention why these numerical examples might look confusing. This is very standard linear algebra. When you estimate covariances from data and try to understand what direction they point, this kind of eigenvalue analysis gives you the right answer. The dimensionality reduction looks a little bit silly when we go from 2 dimensions to 1 dimension. But in truly high dimensional spaces, it has a very strong utility. Here's an example that goes back to MIT several decades ago on something called eigenfaces. These are all well-aligned faces, and the objective in eigenface research has been to find simple ways to describe different people in a parameter space in which we can easily identify the same person again. Images like these are very high-dimensional statistics. If each image is 50 by 50 pixels, each image itself becomes a data point in a 2,500 dimensional feature space. Now obviously, we don't have random images. We don't fill the space of 2,500 dimensions with all face images. Instead, it's reasonable to assume that all the faces live on a small subspace in that space. Obviously, you as a human can easily distinguish what is a valid image of a face and what is a valid image of a non-face, like a car or a cloud or a sky. Therefore, there's many possible images you can represent with 2,500 pixels that are not faces. So research on eigenfaces has applied principal component analysis and eigenvalues to the space of faces. Here's a database in which faces are aligned, and a researcher, Santiago Serrano, extracted from it the average face after alignment on the right side. The truly interesting phenomenon occurs when you look at the eigenvalues. The face on the top left over here is the average face, and these are the variations, the eigenvectors that correspond to the largest eigenvalues over here. This is the strongest variation. You see a certain amount of different regions in around the head shape and the hair that gets excited. That's the second strongest one, where the shirt gets more excited. And as you go down, you find more and more interesting variations that can be used to reconstruct faces. Typically, a dozen or so of those suffice to make a face completely reconstructible, which means We've just mapped a 2500 dimensional feature space into a perhaps 12-dimensional feature space, on which we can now learn much, much easier.